In this course, we will be using the tools we covered in Course 10 to apply some optimization techniques to our app. Once you have identified that there is a performance problem in your app, you want to take these steps to increase performance. Practice good scene management. Generally, drawing fewer objects is good for both CPU and GPU performance, so try to do manual scene management by hiding and unhiding objects through blueprints. In addition to manual scene management, UE4 has its occlusion culling feature. This feature deduces which draw call is completely occluded by asking the GPU how many pixels a draw call produced. Occlusion culling is enabled by default. It is located under Project Settings, Engine, Rendering, Culling. Besides improving culling, another way to reduce draw calls is to combine multiple meshes into one big mesh. This is a trade-off between render thread CPU time and culling efficiency. A poor culling efficiency means we submit more triangles for the GPU to render. Next, we need to look out for GPU bottlenecks. If your application's GPU workload takes longer than the target frame time, which is 13.88 milliseconds for Quest, 12.5 milliseconds for Rift S, and 11.11 milliseconds for the Rift, then your application is GPU bound. Both the CPU and GPU needs to be under the target frame time for the app to be performant, but GPU is intentionally mentioned ahead of CPU because GPU bottleneck can affect the frame time reported by CPU profiling tools. It's a good idea to address GPU performance issues before addressing CPU issues. This means the workload submitted to the GPU will need to be reduced first. In the context of game development, GPU workload consists of a series of draw calls that compose the scene. A good way to figure out which draw call requires attention is to use RenderDoc. Please refer to Course 10 on how to make captures with RenderDoc. For more information on RenderDoc, we have provided additional learning material linked below this video. Once a capture is made, developers can click on the clock icon to measure each draw call's duration. On the Oculus Quest, developers might notice that the sum of draw calls doesn't add up to match the total frame time. This is because of how Tile GPU works. All draw calls for a frame are executed together, making it impossible to measure each individual draw call's contribution. Despite this, it is still a good indicator of relative performance. Once a draw call is identified, there are two main components that contribute to its performance impact: vertex operations and fragment operations. You can improve vertex operation efficiency by reducing the associated mesh's vertex count or optimize the associated vertex shader. For fragment operation efficiency, try optimizing the associated pixel shader, reducing texture usage, or reduce render target dimension. We'll explain these later in this module. The Oculus Quest executes draw calls in two stages, binning and rendering. During binning, a simplified version of the vertex shader is executed to calculate a primitive's position and be assigned a corresponding partition on the render target. During render, every vertex shaders of draw calls that were assigned to a bin are re-executed to calculate any interpolant values used by fragment operations, followed by the fragment shader execution. Because of the double execution of vertex operations, vertex count should be kept to a reasonable amount. This also means that more complex vertex operations such as GPU skinning or vertex displacement will be double executed. There is no need to reduce vertex operation to a minimum, but developers should be aware of the double performance impact nature of vertex operations on the Quest. On the Oculus Quest, Dead and Buried 2 had about 75,000 vertices per frame total, and 700,000 triangles on the Rift. This will vary based on graphical quality as well as how a scene is composed, which is determined by what kind of experience it is. On Rift, developers should feel free to use the more advanced features UE4 has to offer, such as tessellation or world displacement, as long as it's in moderation. The more complex your materials are, the more likely it will result in computationally expensive fragment operations. Therefore, you should set your materials appropriately depending on your graphical needs. One source of fragment operations performance impact is fetching a texture from memory. This means the use of textures in the material should be kept to a minimum because textures can greatly increase the performance impact. On the Oculus Quest, it is recommended to use 2 or less textures per material. Wherever possible, avoid using textures if you do not need to. If you can represent the texture's content by either constants or a simple mathematical operation, do that instead of encoding the data in textures. This will help keep the project's performance impact as low as possible. Make good use of the normal map for lit material, but don't supply a normal map if you want your object to have a perfectly flat surface. It's also a best practice to use as little dynamic light as possible. Just like in scene management, when you are no longer looking at a scene that requires lights, disable them or hide them. This applies to scene components such as facades or backgrounds. Simply not looking at dynamic lights is not enough to eliminate the performance impact of that light on Quest, because it will still enter into the calculation. Normally, game engines find out which draw calls are interacting with which light through a simple volume intersection test. The reason is that by associating each light with a finite bounding volume, each draw call can find out if it needs to invoke the code for calculating lighting for a particular light. By removing light contributions that do not interact with a draw call, the fragment operation will become much more efficient. Currently, however, mobile forward lighting in Unreal doesn't support culling dynamic lights. Static lights have their contribution pre-culled and are also cached, which helps with optimization. Because UE4 supports a wide range of platforms, the default settings are not always the most optimal for VR development. Here are some easy ways to check for what will help with GPU fragment performance. If the material is using a lit shader and specular highlight is not needed, check the fully rough checkbox. This is not the same as setting the roughness pin in the material with a value of 1, because the fully rough checkbox takes advantage of the fact that roughness is 1 and algebraically simplifies the specular highlight calculation. Artists might be tempted to use the high-quality reflections in the materials detail section because of how nice it looks, but this can be very computationally expensive and should be used sparingly. This is related to specular highlights. UE4 uses cube maps to create the illusion of reflection for shiny surfaces. This feature is supported for both the Quest and the Rift. This feature is implemented very differently between the two platforms to accommodate the differences in hardware. On the Oculus Quest, make sure mobile HDR is not enabled, or that if you're using 4.25 or above, enable single-pass linear rendering. The Quest's enormous resolution requirement means a huge amount of fragment operations are executed to calculate the pixels you see on screen. To alleviate this problem, the Quest supports fixed foveated rendering, which reduces the actual number of fragment operations by reducing the resolution in your peripheral view. You can control FFR with the Set Fixed Foveated Rendering Level blueprint node. FFR is not yet supported on PC. Note, FFR is mentioned in Module 10 as a way to maintain a consistent performance scenario for effective comparison. FFR is suggested here as a way to mitigate fragment shader costs because it can be dynamically tuned based on the scene. For example, movement will make artifacts in peripheral vision less noticeable, and therefore the game can adjust the FFR level up as a way to reduce pixel operation in the peripheral view. Next, we will want to identify if there is a CPU bottleneck. There are two common scenarios where an app can be CPU bound. One is bound on the main thread, the other is bound on the render thread. Developers should be careful when determining if the application is main thread bound or render thread bound. A GPU bound application can have a large render thread time, so it is important to rule out the possibility of GPU bottleneck first. If it is determined to be a main thread CPU bottleneck, use StatGame in the console to see which subsystems are contributing to the CPU cost. For example, world take time consists of total CPU cost of advancing the game world 1 unit forward in time, while spawn actor is the total CPU cost of spawning actors in the game world. For more information on other events, please refer to the Unreal Stat Commands documentation we have provided a link to. It's impossible to give a comprehensive description to all the stat events in UE4. Developers will have to become familiar with game source code to learn what all the events mean. Another common scenario is when the application has complex logic implemented using the blueprint system. If this is the case, make sure blueprint nativization is turned on. Using StatGame and check for blueprint time is a good way to see blueprint logic cost. If it is determined to be a render thread CPU bottleneck on the Quest, make sure project settings, engine, rendering, VR, mobile multiview, and mobile multiview direct is enabled. This will reduce the computational cost of draw call submission on the CPU by 50%, but the GPU workload remains the same because it doesn't change the actual number of vertices and pixels getting rendered. Multiview allows one draw call to draw to 2 eye buffers instead of submitting one draw call per eye. The main source of CPU render thread time is the number of draw calls. One way to reduce draw calls is to combine multiple meshes into one larger mesh. However, this is counterproductive to your culling efficiency because a draw call level bounding box check is performed to reduce draw calls that don't show up on screen. If you are not GPU bound and can spare some GPU cycles, consider combining multiple meshes into one bigger mesh at the expense of coding efficiency. If this is not possible, reducing scene complexity will ensure your draw call count is under a reasonable amount. For Quest development, it is recommended to be under 50 multi-view draw calls. Multi-view is an Oculus Quest feature that allows single draw call to be submitted for the two eyes in VR. Cross-platform guidelines for Rift and Quest. For developers who wish to develop for both the Rift and the Quest, it will be worthwhile to leverage UE4's existing cross-platform compatibility and reduce platform-specific special cases as much as possible. Here are a few guidelines. If lighting is desired, both platforms should rely on light maps for static scene objects that don't move. Rift will be allowed to use post-process, have more dynamic lights, shadows, and tessellation. Quest should use a different set of materials, but reference the same or lower resolution texture with lower lighting quality. The reason for this is the Rift and Quest runs two different renderers. If there is a need to address GPU performance via reducing the shader or material resource cost, having Quest and Rift materials separately prevents accidental modification of one platform while trying to optimize the other. And finally, Quest should also use a different set of meshes that have a lower vertex count.